Okay, so real quickly, in regards to a determinant, there's two really important ideas here in my definition. First one, a determinant is a real number. So unlike the other operations that we've kind of been doing with matrices, adding, subtracting, scalar multiplication, matrix multiplication, inverses, we've always been getting another matrix. And if you calculate a determinant, you just get a number. Okay, so it's not a matrix. And determinants only apply to square matrices. So we had talked about yesterday, you can only find inverses of square matrices. You can also only do determinants for square matrices. Now, we're going to do some notation and calculations. So we're going to start with a 2 by 2 determinant. There are two ways that we can write out that we're doing the determinant or to represent a determinant. Okay. So the first way to show that you're talking about a determinant is to write out DET followed by the matrix you want to take the determinant of. So when I see DETA, I would read that as the determinant of A. And if you went to your matrix menu in your calculators and you looked in that math menu where we got reduced row echelon form, you should see a DET in there. So you could calculate a determinant in your calculator by just selecting DET from the math menu and then choosing a matrix. Okay, of course, it has to be a square matrix. Okay, or you get an error. So that's how we see it in our calculators. Has anybody confirmed it's DET in the calculator? Okay. The other notation for a determinant looks a lot like something we've seen before in math. It looks like absolute value, but it's just a set of vertical bars. And when we're working with matrices, instead of calling it the absolute value of A, we call it the determinant of A. So another notation for the same thing is two vertical bars. Notice this is different than the matrix brackets. So if you see, instead of matrix brackets, if you see vertical lines, that's also like an order or a direction to do a determinant. So it doesn't mean the matrix, it means the determinant. Okay, and then if you're calculating the determinant of a 2 by 2 matrix, this is going to look very familiar. The determinant of a 2 by 2 matrix is AD minus, you can fill in the blanks, BC, the difference of the diagonals. So yesterday we talked about AD minus BC when we did the inverse of matrix A, where we would do 1 over AD minus BC. But we could really now rewrite that 1 over the determinant of A. We realize the determinant of A is AD minus BC. So then we could also amend, remember that question, that follow-up question I asked you yesterday? When does a matrix not have an inverse? When that denominator piece equals 0, we said when AD minus BC equals 0, when AD and BC are the same value. So now we can also say when the determinant is 0, there is no inverse. Okay. So I'm going to show you on the next slide, just real quick, one example, and then I'll have you practice a couple others. Okay. So I just want to show you kind of like notations here, or different things that you can see. Suppose A is the matrix 1, 2, 3, negative 1. And I'm being asked to calculate the determinant. So I can write the determinant of A equals, and then, remember, I can show a directive to do a determinant by replacing the matrix bars with the determinant bars. So not only can you put like the capital letter in the vertical bars, you can also put all the entries in the matrix. So if I didn't have determinant of A equals, and if I didn't have my directions at the top, if I just gave you this piece right here, you guys would read that as the determinant of that 2x2 matrix, and you would calculate it. So those are just like different ways that we could notate that. And then I'm going to actually calculate it. So my first diagonal is going to be -1 minus, my second diagonal is 6. So the determinant of A is -7. And again, notice, the answer to a determinant is not a matrix. It is just a number. So I don't know that you necessarily have to write all of these 2x2 determinants down, but at least have a conversation with your groups. What is the value for the determinant? How are you calculating them? Am I getting close? Thank you. Sorry, I missed my little navigator thing. Okay, so see if you can calculate the determinants for B and C. I could show the determinant B by putting the capital letter in between those two vertical lines. So again, I'm just kind of playing around with different notations. And then if I were doing the determinant of B, I would do 10 minus 0. So that's equal to 10. So I have a negative determinant over here in A. I have a positive determinant for B. And then what's our determinant for C? I heard a 0 out there. 12 minus 12 is 0. So which of those matrices don't have an inverse? C. So we can tell just by calculating the determinant. Okay? So there's really like 3 possibilities for determinants. Can be positive, can be negative, can be 0. Okay. 3 by 3. 3 by 3 is going to involve a little bit more work, as 3 by 3 things tend to do. You don't have to do 3 by 3 inverses on your own. Remember, that's in your calculator. However, you can do a 3 by 3 determinant. Now, if you look up in the textbook in section 8.4 how to do a 3 by 3 determinant, it's going to give you a different method which uses something called like cofactors and cominors. It's not quite as simple and easy to run through, so I prefer my method. And this will work for 3 by 3 but doesn't always work for higher square matrices. So you might think about like, okay, could I just do what I did on the last problem, which is subtract the product of the diagonals? But could you imagine, like, if you did this first diagonal, AEI, and then you subtract the second diagonal, CEG, that there are some entries in the matrix that never get used. Okay. So what that means for us is in order for us to calculate our determinant, we need to kind of introduce those values as other diagonals. So we're going to do 3 diagonals each way, so a total of 6 diagonals, when we do a 3 by 3. We're going to do AEI, and then if you could imagine momentarily, if you're having trouble with the 3-dimensional, it's okay. Imagine this matrix was 3-dimensional, so I could go around it. Then I'm going to do BF, and I'm going to wrap around my matrix and come to G. And then I'm going to do C, wrap around my matrix, DH. But an easy way to do that so you don't have to visualize it is just copy your first 2 columns. Okay? Because like if you don't copy your columns, you run out of numbers for your diagonal. But if you copy your first 2 columns, you'll be able to go down the whole diagonal. Now, you could copy the 3rd column, it's just none of your diagonals are going to touch it, so you don't really need to. Okay.
Oh, I see.
So I'm doing AEI plus BFG plus CDH. Okay, So I gotta add up all three of those diagonals. And then I'm gonna subtract from that CEG plus AFH plus BDI. And I'm going to subtract all of that, so I'm going to put in parentheses. So like you can think about here, if your determinant is full of numbers, that's pretty easy, right? You get three different products, add them up. Get three more products, add them up, and then subtract the two. Okay. So we're going to practice calculating a determinant for a 3x3 matrix. You don't really have to like memorize those letters over there. You just kind of have to remember, like, know what to do, right? So let's calculate the determinant for this matrix A. Now you can imagine, some of you may have experienced this in your row echelon form. You can imagine what, like if you're copying it down and you just drop a negative, what a sad day that will be. Because then you won't get the right answer. Just be really careful when you copy it down. And then you also have to be really careful. I've been known to do this when I copy my first two columns, dropping a negative. That'll be really annoying too. So I know I want to calculate the determinant. I'm going to copy my first two columns. I really need to copy the third because none of my diagonals will get there. And then I'll show you, I really like to kind of keep track of my work like this. So like tomorrow when you guys are talking with your groups about your homework, you can compare like the numbers you got on the diagonal. So if your answers don't agree, you'll be able to say, well, what were your diagonals? It's really easy. I just go down, multiply. So 1 times negative 1 times 0 is 0. I just write that right under the diagonal, plus negative 2 times 2 times 1. Negative 4, plus, I love any diagonal with a 0 in it because it's 0. And so that makes it real easy. I just add those up and I get negative 4. Then just go on the diagonals the other direction. So I go up so I can put my numbers up there. 1 times negative 1 times negative 1 is 1. Negative 2 times 2 times 1 is negative 4. And then, of course, I got zeros here, so that's going to be a 0. So that's a negative 3. And I'm always subtracting those two numbers. So it's negative 4 minus negative 3, bless you. Which gives me negative 1. So, I mean, it is more work, but it's really not terrible work, right? Now, you can imagine if your matrix was filled with fractions, if your matrix was filled with large numbers, if your matrix was filled with decimals, what might you use? A calculator. Okay, so just like kind of keep that in mind. If you're working with really big numbers, if you're working with decimals, if you're working with fractions, if you're working with a matrix higher than a 3x3, you should use your calculator. Okay, so you don't have to write that down, but just kind of like make a mental note. Okay, you could use your calculator to do that determinant. Now, that's basically the end of 8.4, which is what you need for your homework assignment tonight. So you'll be calculating determinants in the homework. But I am going to have you jot down a few things from 8.5. This will alleviate some of the work that we do on Thursday with Kramer's rule. We can focus on solving the system. And these things, they use the determinant. So these are applications of the determinant. Why would I ever want to find the difference of the diagonals? What is the point? Here's 3 uses for the determinant. This is from section 8.5, so you actually won't have any homework assignments tonight over these problems. They'll be on your Thursday assignment. But then it makes Thursday really long, and today is really easy, so it's easy to add that today. They're like ahead of schedule. Good. These are applications or uses of a determinant. Why would we ever want that real number associated with a square matrix called the determinant? That's a plus or minus 1/2. Thank you for asking. No, that's okay. Okay, now there is a proof of this area of a triangle. I'm not going to take the time to do it because it's not necessarily one of the nicest proofs to run through. Probably put 3/4 of you to sleep. So if you're curious, I think the proof is in the book at the back of chapter 8. Or you could come in and see me before after school if you want to examine that. But we're just going to accept it as truth. Okay. So notice in the setup over here on the right, that's not a matrix because it has just vertical bars. So that's asking you to calculate a determinant for those 3x3 entries. And so we know that like all of this that's set up right here, this is just going to equal some number, right? Because we're going to calculate the determinant. And then we're just going to multiply it by plus or minus 1/2. Now, you're not actually going to multiply it by both positive and negative 1/2. Okay. You're going to choose positive 1/2 or negative 1/2. So you only multiply it by one of them. But if we're talking about area of a triangle, we would argue from geometry that the area of a triangle should be positive. So if you get a positive determinant, multiply by positive 1/2. If you get a negative determinant, multiply by negative 1/2. Your area in the end should be a positive number. And what, like if you want to think about this visually, so we've got 3 vertices. I just plotted 3 points over here on the sideboard, just so you can kind of see. Put 3 points anywhere on the coordinate plane, connect them, you get a triangle, and we're finding the area inside that triangle. You could imagine the kind of work we would have to do, like in geometry, we'd have to do distance formula, maybe some midpoint formulas, employ the area of a triangle, 1/2 times base times height. So that could actually end up being a lot of work, but we're saying just do plus or minus 1/2 times the determinant. And then with your 3 vertices, just make a row for each one. That last column, you're just going to fill in with a 1 every time. It doesn't matter what order your vertices are. So Jackie could do different x sub 1, y sub 1 than Eli, and we're going to get the same answer in the end. So you never have to stress about what's x sub 2, y sub 2. It doesn't matter. Okay, now I had said like how to choose positive or negative 1/2. I said if the determinant was positive, choose positive 1/2. If your determinant is negative, choose negative 1/2. What's the other possibility for your determinant? Could equal 0. If your triangle's determinant was 0 and the area of your triangle is 0, what could you really say about said triangle? It's really a line. Okay. So you can also like use this picture I have over here on the sideboard. I'm going to take this vertex right here. If I asked you to make this triangle a smaller area, I would just take this vertex and I would start moving it closer to the other side. Because then my triangle becomes like a sliver of a triangle. And then all of a sudden when I put that point on the other side, is there even a triangle? No, there's 3 points on the same line. So we can also use the determinant to test for collinearity. All the geometries. Because you don't know about matrices. Okay, so the test for collinearity really kind of piggybacks off of the area of a triangle. In order for your 3 points to be on the same line, that means they're actually not a triangle. So then the determinant has to equal 0. It's the only way those 3 points will be on the same line. If your determinant equals anything besides 0, then you could multiply by plus or minus 1/2 and you could get an area of a triangle, however small that may be. Okay, so that would mean that they are not collinear. So I'm going to use a little bit of geometry jargon here. I'm going to say points are collinear. Do you remember if and only if? IFF? If and only if the determinant of A equals 0. So that's really what you're checking. So if I ask you, are these 3 points collinear, basically do a determinant. If it equals 0, say yes. If it doesn't equal 0, say no. Done. So when I do the test for collinearity, I don't need that plus or minus 1/2 that actually calculates the area because I'm not interested in the area. I'm just interested in if it's collinear. Now, that's for 3 individual points. I want to see if those 3 points lie on a line. If I wanted to write an equation of a line, how many points would I need to write an equation of a line? 2, because through any 2 points anywhere in space, I can draw a line connecting them, right? And so, piggybacking off of the test for collinear points, I can also use a determinant to write an equation of a line. So it looks very similar to the test for collinearity, but the big change is instead of 3 points, there are 2. And then I have an X and a Y in there. So if I asked you to give me examples of equations of lines, you might throw things out in slope-intercept form. Y equals mx plus b, like y equals 3x plus 5, y equals 1/4 x minus 2. Or you could give me something in standard form, like 3x plus 4x equals 12. In all of those equations of a line, you have to have an x and a y. So one of the points that we used to like sub in numbers for are just going to be the letter x and the letter y. And that means when I calculate my determinant on those diagonals, I won't always get numbers. Sometimes I'll have x terms, sometimes I'll have y terms. But those will come together to be the terms in my equation of a line, and those will be my variables, the x and the y. So we'll do an example so you can see what that looks like. Okay. But just know you'll only get 2 points for this, so in the other row of your determinant, you'll just have to plug in x and y, okay, as letters. Don't put in numbers. And that could really be on any line. It doesn't have to be at the top. You'll still get the same equation, but I always put it at the top. Okay, so let's just practice some examples. Okay, see how we can do these things. So here's an example. Find the area of a triangle with vertices at these points. 0, 0, 4, 1, and 2, 5. And I'm working in my matrix chapter, and I just learned about determinants. So I know I can find the area of a triangle using a determinant. So I'm going to set that up. So each row is a new point, 0, 0, 4, 1, 2, 5. And for that last column, because I can only do a determinant of a 3 by 3, I just put in a 1. And we know that to calculate the area of a triangle, in addition to the determinant, we're going to have to do plus or minus 1/2. So we'll just have to know that. And I won't be able to decide if it's positive or negative until I calculate the determinant. I need to know what the determinant is. So I'm going to copy my first two columns. Start calculating. So 0, 0, and 20. And on the other diagonals, 2, 0, 0. Plus or minus 1/2 in there. Then I had 20 and 2. Okay, you're always subtracting the product of the diagonals. So the determinant in this matrix is 18. To calculate the area, should I multiply by positive 1/2 or negative 1/2? Positive 1/2 to keep it positive. So I can say that the area of my triangle is 9 square units. And I'm done. So like you're thinking ahead to your test, you're going to need to study, do the determinant, multiply it by plus or minus 1/2 if I want the area of a triangle. I've got to know that. Okay, let's do an example where we test for collinearity. What are we going to look for if we're testing for collinearity? Does the determinant equal 0? And then it's a simple yes or no question. So I get 3 points. I know I can use a determinant because I'm working on my matrix unit. That's what I learned about the determinant. So put in the 3 points, each in their own row. Last column is 1s. Copy the first 2 columns. And calculate. So I get -2 plus 24 minus 12, so that's 10. And I get 6 plus 8 plus 12. Uh-oh. The only way this was going to equal 0 is if my red diagonals add to 10. Now that I've done my blue diagonals. So now my red diagonals, 14 plus 12, that's 26. Are these collinear? Okay, that's equal to -16. That's not equal to 0, so it's not collinear. If they're not collinear, that means if I plotted those 3 points and connected them, they would form what? A triangle, and I could then calculate the area of the triangle. Since my determinant was -16, multiply by -1/2, the area of my triangle would have been positive. But I don't have to go any further. If the check is for collinearity, you just say yes or no. Okay. And then one last example. We'll write the equation of the line. Bless you. Okay. Again, I learned about this in my matrix unit. I can use a determinant. So I'm going to set up a determinant again. Because I only have 3 points, one of my points are just going to be all the points on the line represented as x and y. And then I'll have -3, -1, 3, 5. My last column is 1s. This is supposed to equal 0, 2, right? Like these 3 points have to be collinear to be on the same line. So there is an equal 0 over here. I'm going to leave some space because I got to copy my columns. But that's where you get your equal sign for the equation of a line, is that it equals 0. Copy my columns. And when you do your columns on this one, you're going to see I can't always add stuff together. So like my first diagonal is negative x. And then I get plus 3y. And then I get negative 15. And none of those are like terms. So I have 3 terms. On my other diagonals, I'll get a negative 3, a plus 5x, and a minus 3y. Again, I can't add any of those red ones together because those are not like terms. When I calculate my determinant, remember I'm taking the sum of the blues, the first diagonal is going down from left to right. Okay, so like negative x plus 3y minus 15. And I'm subtracting from that the sum of these. So these should all be protected by a set of parentheses. So like remember, what you're not just going to like combine like terms negative 3 and negative 15 and get negative 18. You're actually subtracting negative 3, which would be adding 3. So those are going to change signs at the top, okay, because you're subtracting all of them. So we're going to do plus, plus, negative, plus. And then I can combine like terms. So a negative 15 plus 3 is negative 12. Negative x minus 5x is negative 6x. And 3y plus 3y is 6y. And it equals 0. That's an equation of a line. Could leave it like that. If you wanted to look like standard form, you could add 12 to the other side. That's an equation of a line. You could do like x-intercept is negative 2, y-intercept is 2, graph it. Or you could do what? Yeah, solve for y-intercept form, but I would say like, why do all that extra work where you could make a mistake? But that would be y equals x plus 2. You might check in the back of the book, like they might take this one and divide it by negative 6. So they could say like x minus y plus 2 equals 0. I'll accept either of them. They're all equations of the same line. So I'm okay with whatever you do. Okay? You have a homework assignment. We're going to do some practice tomorrow. Take a breather with all this matrix stuff and practice. And then we'll do our final matrix notes on Thursday.